Okay, so ambiguity, that means you can have the same string generated by the grammar that has at least two different parse trees. Okay? Definition of ambiguity. And if you have two different parse trees, that usually means two different meanings. Now, in the context of computer science, like a compiler or something, that's a disaster, right? Like for a programming language, a program should have a unique meaning, a unique interpretation. It's just one thing. You're asking the computer to do something, and you want it to do one thing. You want the computer to interpret your language, your computer program, your set of instructions telling the computer what to do. You want that telling to be unambiguous. You want it to be unique. There's only one interpretation, right? So you don't want two different parse trees for the same string, right? So ambiguity can be a problem for grammars. So it's a topic that we have to deal with. All right. Now, okay. So ambiguity is when you have the same string with two different parse trees. You say that a grammar itself is ambiguous if it can, that grammar, generate a string with two different parse trees. Okay? So if the situation of ambiguity arises, in other words, same string, two parse trees, and that ambiguity is generated by a grammar, that grammar is said to be ambiguous. So you can have an ambiguous grammar, right? Now let's do an example. It's getting a bit dark. Perhaps I should put on my cap and switch on the light just a minute. My wife still has a lot of clothes drying. It blocks off the light. Alright, so here's an example of another grammar. It's slightly different. It's G5, so G for grammar, our fifth example of a grammar. It's a sort of simplified version of G4. It does not have parentheses. And you will see that it is ambiguous. The grammar is ambiguous. Why? Well, because it generates a string. You don't have to generate one string. For a grammar to be ambiguous, it's sufficient, it's enough, for it to generate just one string that has two parse trees. Okay, that's enough for that grammar to be labelled ambiguous. It's a bad thing. Right. Okay, so G5 here. And remember earlier sessions saying in practice a grammar tends to be specified often simply by its rule set. That's it. I mean, strictly speaking, a grammar, formal definition of grammar or specification of grammar, you need like four things. You need that for tuple, remember? Capital V, capital sigma, big R, a set of rules, substitution rules, and the start state. Okay, but you can get three of those four just from the rules. So often in practice people talk about a grammar and they'll just give the rules. Okay, so that's what we're going to do now. So here's this grammar G5, and here's its rules. Okay, here's the rule set. In fact, how many rules are there? It's just 1, 2, 3, 4. That's it. Four rules in the substitution rules set. Okay, well, there's only one variable, so it has to be the start variable. So start variable is EXPR. That's short for expression. In fact, which is short for arithmetic expression. Right? It's G5, similar to G4. G4 was about arithmetic. It was the grammar generating strings of arithmetic expression type. Right? So here are your 1, 2, 3, 4 substitution rules. That together, that's your R, big R. Okay, here's the string that we're going to show is ambiguous. It has two different parse trees. Okay, so we can parse this ambiguously. Now here's one way. Oh, by the way, I keep coming across this. Sipser uses parse trees in a way that I don't think is very smart. I prefer, so you can call this the deGaris tree, right? The deGaris method, and versus the Sipser method. I prefer this way because it's clearer which substitution rule got used, right? Like for example, using my method, it's clear that this goes to this one. So in other words, you use expr arrow this one, right? This is what you substituted instead of expr. Okay, so it's clear there. And then the vertical line tells you, well then this got changed to, got overwritten if you like, to expr plus expr. Okay, and then that got overwritten by A, and that got overwritten by A, and then again that's just me. I put these little dots that connect the, on the bottom line. So the bottom line here is the string of terminals. Remember when you derive a string of terminals, and I put the little dots here to indicate where this terminal symbol came from. Well, it came from up here. Now, can you see the critical choice in these two different parse trees was whether you substituted the multiply times rule first, or did you substitute for this one the plus rule first? Right? So in other words, did you apply this one first, or did you apply that one first? Okay, that was the critical difference between these two trees. So now you can see you get the same string, right? They work out the same string, but this branch of the tree, if you like, is the A times A, and this branch of the tree is like the plus. So in a sense, these three symbols are grouped into the left branch of the tree, whereas these three symbols are grouped into the right branch of the tree. But it's the same string. The structure, you can just see, just visually, you can see the structure of these two parse trees, quite different, okay? And therefore, you have ambiguity, okay? So, I guess that leaves you with a problem, right? Let me just check further on the text. How often do parse trees pop up in the text? Let me see if I can just visually. I'm not seeing too many actually, because pretty soon we'll be getting into computability, which is mostly Turing machines. So maybe it won't be such an issue in practice. Okay. Yeah. Well, anyway, the question you're left with is, it's up to you. Do you use the Sipser method to draw parse trees, or do you use the deGaris method? Well, what's the difference between the deGaris method, this method, and the Sipser method? Well, the Sipser method, he would have this. You see.